Okay, students, Assalamu alaikum. Can you hear me properly?
Walaikum Assalam. Yes, sir.
Okay. I uploaded the material related to the course yesterday night, and that was about chapter number 2. I uploaded the PDF of the PowerPoint slides, and as well as I uploaded the textbook which we are using for this course. The fifth edition of it we are using in this course, so I uploaded that as well as I uploaded some material related to the assignment, and then the assignment number 1 itself I uploaded. So I hope you're able to get all the material. Were you able to access the material?
Yes, sir. We were.
Yes, sir.
Okay. We're going to discuss about that material later on. Right now, what we're going to do is we are going to continue with the chapter 1 where we stopped, and by the end of chapter number 1, we are going to discuss the assignment material and the things related to that. So, first of all, my previous lecture with you guys, do you have the video link for it?
Yes, sir, we do.
You have the video link for it, because I'm getting mixed responses. Some students say that they don't have the access to the video link. Some students says that yes, they have the access. I'm not sure what is true. So you can watch my previous video for the first lecture, right?
So did you upload it? Upload the link?
Sir, where is the link?
No, I'm not sure, because it's automatically does the video recorded automatically does not go into the Google Classroom folder. Is
So
there
let me
anybody?
check.
Is there anyone who tried to access the video?
So when you're done recording, you will get an email for the recording, and then you
Yeah,
have to upload it.
I got an email, and then there is a folder recording meeting in the Google Classroom from
Yeah,
where.
you have to share it with us. We can't
So
watch it without your
it's
permission.
not automatically shared with you.
No, no.
Okay, okay, خلاص, I'm gonna do that. Okay, so let's continue with our, as I told you, right now we are going to continue with our chapter number 1. After chapter number 1, we're going to discuss about the assignment material that I gave you, and any other issues.
Okay.
Can you see the shared screen for the slides of chapter number 1?
Yes, sir, we can.
Okay. So we were discussing about pressure, and I gave you an understanding about the absolute pressure. Okay, and absolute pressure is a pressure which can never go negative. The minimum possible was that it can be absolute zero or absolute vacuum, absolute zero pressure, or which is absolute vacuum. And then I gave you an understanding about the atmospheric pressure and the gauge pressure. I told you that the gauge pressure is basically uh, the device, the pressure measuring device, which measures the gauge pressure. It just gives you uh, a pressure relative to the atmospheric pressure, so it will give you the value how much a pressure is higher than the atmospheric pressure. And then we have the vacuum gauge devices, which can measure the pressure again relative to the atmospheric pressure, that how much lower than the atmosphere pressure is, that will be the vacuum pressure. So there is a relationship between absolute pressure, there is a relationship between absolute pressure, atmospheric pressure, and gauge pressure, as well as there is a relationship between absolute pressure, atmospheric pressure, and vacuum pressure. This was shown through the figure here, okay, and at the same time the we have the mathematical formula which mentions about this relationship. Okay, so before moving forward, I first need to know, did anybody go through the lecture and did you find any problem in the understanding about any topic so far that we have gone through? You are free to ask.
No, so there weren't any problems for me.
Okay. Anybody else who feel that you do not understand any topic, anything? Just try to understand one thing, that in this course, things are building over one another. Okay, so if you have issues, then it's better to resolve now rather than accumulate it with other topics and with other issues, and then it will become difficult for you. Okay, so let me know. Okay, don't ever be shy with me in this regard, that okay, the doctor will taunt you or say anything bad. No, it's okay. If you are willing to learn, I'm willing to teach, no problem. Okay, so you have any issue about anything, just feel free and let me know. Okay, inshallah we're going to resolve the issue. So then if nobody has any issue till here, then we can continue forward. Okay, so let's see this problem. We have a vacuum gauge. So first of all, it is a device which measures the gauge pressure, the vacuum pressure. We have the vacuum gauge connected to a chamber that reads 5.8 psi at a location where the atmospheric pressure is 14.5 psi. So atmospheric pressure is 14.5 psi. Determine the absolute pressure in the chamber. Okay, so we are given the atmospheric pressure, we are given the gauge, the vacuum pressure, and we want to find out the absolute pressure. Now, knowing the relationship between absolute pressure, atmospheric pressure, and vacuum pressure, it's nothing more than just substituting the values and getting the result. Okay, so it's the same. Now, one question arises that suppose if you have a paper-based exam, will this formula, these two formulas be provided to you? So the answer is no. These two formulas will not be provided to you. They refer to the conceptual understanding of a gauge pressure with the absolute and atmospheric pressure, and the vacuum pressure with the atmosphere and absolute pressure. Okay, so there is a conceptual understanding of it, and I want you to have that understanding with you. These formulas will not be provided to you in the exam, if I'm talking about the paper-based exam. So, but if you know the formulas, if you know the relationship, then there's nothing more into it, just substituting, plugging the values in, and then getting the result. Is this question clear? Anything which is not clear?
Yes, sir. Yes, sir. It's clear.
Okay, the absolute pressure inside a tank is 0.2 bar. So what's given is this absolute pressure is 0.2 bar, and the surrounding atmospheric pressure is 101 kilopascal. Now you see here one thing, the pressure for the atmospheric pressure is given in kilopascal, and the one inside the tank is given in bar. Now you see here, if you remember, I told you in the last class that there were two lines where you have the unit conversion between bar and kilopascal and megapascal and atmosphere. Okay, so this conversion is very important because you're going to have this conversion a lot of time in the course. Okay, and it's better to have this thing on your fingertips. Okay, so if this thing is on your fingertips, you can really do it easily. Otherwise, it's going to become very, very difficult. So 1 bar is 100 kilopascal. So 0.2 bar will be like 20 kilopascal. Okay. So the thing is that the question is that what reading would a pressure gauge mounted on the tank will give in kilopascal? So we want the answer in kilopascal. So it's better to convert 0.2 bar into kilopascal. So that will be 0.2 bar will be 20 kilopascal. Okay, so now we have the absolute pressure is 20 kilopascal, atmospheric is 101, absolute is less than atmospheric, means this is the vacuum. This will be the vacuum reading. Okay, so what will be the vacuum reading? How much it would be? It would be the difference between the two. So, okay, so again, the same formula we will be using. So we want to find vacuum, and we are given the atmosphere. We are given the atmosphere, and we are given the atmosphere reading, and we know the absolute reading. So we want to find out the vacuum reading. So same formula, but just plug and play. That's it. But the unit consistency is very important. Remember, in an equation, the equation should be completely homogeneous. So if everything is in bar, then everything should remain in bar. Then your answer should also come in bar. If everything is in kilopascal, then everything should remain in kilopascal, and then your answer will also come in kilopascal. Is this thing clear so far? Is there anything within the concept here which is not clear? Please ask.
Clear, sir.
Okay. Students, I want you to be responsive, okay? So whenever I'm teaching, I'm going to be continuously asking questions, okay? Or asking you whether you understand it or not, and I need a response from you. If yes, yes. If no, no. But I need a response so that I know that, yes, you are actually catching up with me.
Sir, I wanted to ask, this question says
Yes,
that
yes.
at the end it says that, is this a gauge of vacuum reading?
Yeah.
Uh,
Is
is
this
it?
a gauge of
I don't think
because you
so.
see, no, it is. You see, we have a gauge. We have pressure gauge reading. Okay, when the absolute pressure is greater than atmosphere. So you see, we have pressure gauge reading when when the absolute pressure is greater than atmosphere, and we have the vacuum gauge reading when the absolute pressure is lower than atmosphere.
Oh, okay, I
Okay,
get it.
okay,
Yes.
okay. So here it says, is this a gauge? Uh, there's a mistake in the question. I'm sorry. Is this a gauge or vacuum reading? It's not off vacuum. It should be or vacuum. Okay. Is this a gauge or vacuum reading? Okay. So,
Okay, that makes sense. Thank you.
Thank you for correction. Okay.
So can you please repeat once again the slide you?
Yes, on the slide, what I've said is that if it is a gauge reading, then the absolute will be greater than atmosphere. Make sense?
Yes.
And if it is a vacuum reading, then the absolute will be lower than atmosphere.
Okay, sir. Okay, thank you.
Okay, make sense?
Yes, sir.
So look here. We have absolute reading 20 kilopascal, atmospheric 101 kilopascal. So which one is bigger?
Assalamu alaikum, sir.
Atmospheric is there.
Atmospheric is bigger. Since atmospheric is bigger, so it will be a gauge reading. Okay, so it will be a vacuum reading. I'm sorry. Okay. Okay. Then we have two more problems here, but I want you to go through them yourself. There is just consider them as exercise problems. There's nothing more into it. Just if you have an understanding of the formula, then it's just plug and play. That's it. Nothing more into it. Okay.
Okay, sir.
Wherever it's written in the question, find out in PSIA in the English units. Just ignore it because English unit I'm not going to consider for the exams. Okay, so it's just there. I took it from the book, but it's okay. You don't need to work over the English units. Okay, so let's have a concept here: variation of pressure with depth. Okay, let's study this topic. Look, suppose if I have a fluid. Okay. Anybody want to ask anything? Okay, suppose if I have a fluid, and let's say the fluid is contained inside a container. Okay, so there will be a free surface. Okay, so this is the free surface of the fluid. The free surface is known as free surface because it is free, it is open to atmosphere, and it is represented like this. You see a small triangle, inverted small triangle. That's the symbol of the free surface. Okay, so if we suppose we have a fluid inside a container, and we have at the top surface as a free surface. Okay, so as we move down, this this container. Okay, as we move down or and away from the free surface, the pressure is going to increase. So pressure is going to increase as we move down, and pressure is going to decrease as we move up. So that's increase, let's say positive pressure, and that's decrease. If we are moving up, the pressure will decrease. If we are moving down, the pressure will increase. First of all, do you understand this thing or not? Is this thing clear? Whenever you have a fluid, when you move down, the pressure increases. When you move up, pressure increases. Pressure decreases.
Yes, sir. Makes sense.
Okay.
Yes,
Okay. Now the next question is that how can we calculate what is the increase in pressure? To calculate the increase in pressure, the formula is rho GH. Rho is the density of the fluid in which we are going down. Okay. G is the acceleration due to gravity, and H is the depth below the free surface. So wherever you have the free surface, just below the free surface, whatever is the depth is that is known as H here. So this rho GH, if you multiply rho with G with H, is going to give us that how much is the pressure rise. Okay, what is the pressure rise if you move down? Okay, so is this thing clear? How do we calculate how much is the pressure rise as we move down?
Yes, sir.
Okay, now there is one thing that you have to understand as well. It says variation of pressure with depth. That means the pressure is going to change if you change the elevation. You move down, the pressure will increase. You move up, the pressure will decrease. But suppose if you are not changing the elevation, if you are talking about having on the same elevation, let's say if I draw a horizontal line here. For the whole horizontal line, it's the same elevation, right? So that means on the same elevation, there will be no change in pressure. So there will be the same pressure here, 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 or here. Okay? So on a horizontal surface, the pressure does not vary. Okay? So if I have a fluid, I just draw the horizontal line, and wherever the horizontal line is, they're going, it will be same pressure throughout. Make sense?
Yes, sir.
Yes. Yes.
Yes.
Okay. Okay. So I told you one thing that as we move down, pressure increases. As we move up, pressure decreases. And if you want to know that how much is the pressure increase or decrease, that depends upon what is the value of rho GH. Okay, where H is how much we're moving down, or if suppose we are talking about how much pressure decrease, if we are moving up, then how much is the H when we are moving up. Okay, so that will be H for that. So we have rho GH. Through rho GH, we can calculate how much is the actual, what is the actual magnitude of pressure going higher or lower. Okay, then the other thing that we said is that the variation of pressure is only with depth. That means if you are at the same elevation, then on the horizontal surface, okay, there will be no change in pressure. If you understand all these concepts here, then it's okay. We are done with this slide. I'm gonna move forward. So anybody want to ask anything?
No, sir, everything's clear.
Okay. Okay, so let's say that I have not try to understand one more thing here. We'll talk about pressure measuring devices. So we have some different types of pressure measuring devices. One is the pressure measuring devices we known as pressure gauge. They are normally the mechanical devices. Okay, I'm not going to go into the mechanism. How does they operate? We're going if you have a course of fluid mechanics, you're going to cover this topic there. That what is the working principle of these kind of gauges. But right now what I'm going to focus is that we have, let's say we have a gauge, pressure gauge, which can measure the pressure. Then we have another kind of pressure measuring device, and that is known as manometer. Manometer is another kind of a pressure measuring device. Let's talk about what is manometer. Manometer is in the form of a U tube. So you have a tube which is in the form of U shape. Okay, so I apologize my drawing, because I'm drawing through the mouse, it's very bad, but anyways. So let's say if I put some fluid into it. Okay, so let's say if I put some fluid into it, so what will happen? The fluid will fill the space. Okay, okay, so let's say the fluid is I put some fluid into it, and you will see one thing, that the fluid maintain its level. Okay, so you'll have the same horizontal level maintained of the fluid. Okay, now suppose if let's say that both ends are open to atmosphere, so both are free. So now suppose, let's say that on one end I increase the pressure somehow I increase the pressure. What will happen when I increase the pressure on one end? Somehow what will happen, the level of water or the level of liquid here is going to go down. The level of liquid here is going to go down, and the liquid level here is going to go up. Make sense?
Yes, sir.
Yes.
Okay, now suppose if I do the opposite thing, I reduce the pressure here. Instead of increasing the pressure at this point, if I reduce the pressure here, what will happen? Now the atmospheric pressure will become more, and so the level of water is going to rise up here and it's going to go down here. Okay, so but by just looking at the level between the two sides of the U-tube, you can just simply tell which side pressure is higher and which side pressure is lower. Now consider this case. You have a tank. This tank has certain fluid inside, let's say a gas. Okay, you connect it with a manometer, and you have a manometer liquid inside. So now what happens is that when the gas comes in contact with the manometer liquid, okay, the other end of the manometer is open to atmosphere. Okay, so it raises up like this to certain level. Okay, so this level is higher than this level. What does this mean? What do you think? The pressure inside the tank is higher than atmosphere or lower than atmosphere?
Sir, higher than the atmosphere.
Hi.
Higher than the atmosphere. Suppose if the water level inside the other inside the manometer in the other tube open to the atmosphere was not here. Let's say the water level was here. Okay, so if the water level was here, that means then the pressure inside the tank would be higher than atmosphere or lower than atmosphere?
Lower.
Lower than atmosphere. Okay, so by looking at the level of water in this U-tube manometer, you can just simply tell that what is the level of pressure. Okay, how much is the pressure, which side pressure is higher, which side pressure is lower. Okay, so this is one thing. Now let's talk about another thing. Can we calculate that how much is the pressure variation between the two sides? Yes, we can. Okay, how can we calculate that? So we have the atmospheric pressure here. Okay, now as we move down this free surface, the pressure will rise. As we said in the last slide, that there is variation of pressure with depth, so pressure is going to rise, and it's going to rise till this level, because this is a horizontal level where the pressure here would be the same as the pressure here. Okay, so what is the difference between the pressure at this point and this point? Is this liquid column height. Okay, that is the pressure difference. Okay, and how can we determine how much is this pressure difference? Is by rho gh. Okay, so whatever the liquid we have within this manometer, the density of that liquid multiplied by G multiplied by H. H here will be what? The height difference between the two. Okay, so that will be H, and by using this formula, you can determine what is the difference of pressure between the two ends of this manometer. Now let's say one end is open to the atmosphere, so the other end would be the absolute pressure inside the tank. So you can find out what will be the pressure inside the tank. Is this thing clear or not? Is this concept? If
Yes,
you have
sir.
an issue, you can ask.
Yeah.
So this is a manometer, okay, and through manometer you can actually determine, because manometer is a very simple device. It's just a small tube which is made in the form of a U shape, and you fill this tube with some fluid, let's say water or mercury, okay, and then on one end you connect it with the tank, other end keep it open to the atmosphere. The level of the fluid of manometer between the two sides of the U tube is going to tell that whether the pressure of the tank is lower than atmosphere or higher than atmosphere, and the difference in the level is going to exactly tell you, and you can calculate that how much is the pressure difference from the atmosphere. So this is kind of a pressure gauge or vacuum gauge. This manometer could be used as a pressure gauge or a vacuum gauge, so that you can find the higher pressure or the lower pressure. So far, is this concept and the working principle of manometer clear to everybody or not?
Yes, sir.
Yes, sir. Clear.
Okay. Okay, so let's have a numerical associated with it. Okay, so we have a manometer is used to measure the pressure of a gas in a tank. So we have this tank and it is filled with a certain gas, and we want to use the manometer to calculate the pressure inside this tank. The fluid used has a specific gravity 0.85. So this manometer, there's a fluid inside this manometer, and that fluid has a specific gravity 0.85. Now, I don't know whether you remember or not, but we discussed about a specific gravity in the last class, that if you know the specific gravity of any fluid, you can find out what is the density of that fluid. Because the specific gravity is a ratio of two densities, density of any fluid divided by the density of water. So you have to just multiply the specific gravity with the density of water, and you're going to get the density of that fluid. So given the specific gravity means you know the density. Make sense?
Yes, sir. Yes, remember.
So the fluid used has a specific gravity 0.85, and the manometer column height is 55 centimeter. Okay, so this manometer column, this height means the difference between the elevation here and here. First of all, when you look at the two sides of the manometer, when you look at the level of the liquid on the two sides of the YouTube manometer, what do you think? The pressure inside the tank, is this pressure higher than atmosphere or lower than atmosphere?
Higher.
Higher than atmosphere. That's why this side is at a low elevation than this side. Okay. Good. So we have this given, this height is 55 centimeter. Now, if the local atmospheric pressure is 96 kilopascal, so it's given that the atmospheric pressure is 96 kilopascal, determine the absolute pressure in the tank. Okay, so we need to find out what is the absolute pressure in the tank. Okay, before moving towards the solution of the problem, first of all, do you understand the problem statement itself or not? Is there anything that you do not understand within the problem statement?
No, sir, it's clear.
No, sir. Clear.
Okay, good. Now, if the problem statement is clear, now let's look at our strategy of solving the problem. Okay, we need to find out the absolute pressure inside the tank. So we're going to start from the side we know. We know this is the atmospheric pressure, and obviously this atmospheric pressure will be applied to the free surface. Okay, so then we have to move down. Okay, so we move down, so the pressure should increase. Okay, so P atmosphere plus, then there will be increase in pressure, and how long we are going to move down till this level. Okay, because at this level, whatever the pressure we have here will be the same pressure, whatever the pressure we will have here will be the same pressure we will have here at this point. Okay, so because this is a horizontal line, you can see here, if I draw a horizontal line here, so that's a horizontal level. At horizontal level, the pressure remains same. So whatever the pressure here will be the same pressure here, and this will be the same pressure of the tank, because the tank is connected to the fluid, to the fluid inside the manometer at this point. Okay, so whatever the pressure here will be the same pressure of the gas in the tank. Okay, so this is the logic of solving the problem. Okay, so if we look here, so the pressure, absolute pressure in the tank will be atmospheric pressure plus rho GH. Okay, for the rho density, we can find out because we know what is the specific gravity. Okay, so specific gravity multiplied by density of water is going to give us the density of this fluid. Then this multiplied by G is 9.81, multiplied by H in, it was given in centimeter, but we use in the basic SI unit, it will be 0.55 meter. Okay. So this thing, rho GH plus P atmosphere, is going to give us the absolute pressure in the tank. Now here one thing, you have to be focused over the dimensional homogeneity. You see here the atmospheric pressure is given in kilopascal, but if you put the values here in rho g h, since you are using the basic SI units, so you're going to get the pressure in the basic SI unit. The pressure in the basic SI unit is in Pascal. Okay, so you cannot add Pascal with kilopascal. Either convert everything into kilopascal and then add, or convert everything into Pascal and then add. But you cannot add kilopascal and Pascal together. Okay, so here what we did is that rho gh is going to give us the value in Pascal, but then convert it into kilopascal, we have to divide by 1000. So now this term is in kilopascal, will be added to atmosphere in kilopascal, so you get the absolute pressure in kilopascal. Is this thing clear?
Yes, sir, it's clear.
Yes,
So,
sir.
sir, I have a question.
Yes.
Sir, is it necessary that we solve every problem in Pascal, or we can go
It's
with
your choice. It's your choice. Look, either it is written in the question that find out the value in this unit, then obviously you have to get the answer in that unit. Okay. But if it is not written, then it's your choice. The same problem could be solved in a different way. Instead of dividing this term by 1000, if you multiply this term with 1000, so you get your answer in Pascal. And
Yes,
it's
sir.
okay. There is no problem in it.
Okay,
Okay.
sir. Thank
Anybody else want to ask anything?
No, sir.
Good. Okay, so this problem is done. Then we have two more problems here. You can just go through it yourself. They are like an exercise problems. Okay, not difficult. Difficult ones we are going to see, inshallah, in the later chapters. There's a problem solving technique mentioned here in the first chapter. But this problem solving technique normally we use in any case. Okay, so you have the known values, then you figure out what you need to find out, then you draw the schematic diagram, then you write down the assumptions, do the analysis, get the answer. I mean, this is a problem solving technique. We are doing it anyway, but anyways, here it is listed down. So you go through this yourself. Okay, there's nothing to be explained in it in here. With this, our chapter number 1 is finished. Okay, there's a summary of the chapter. You have some practice problems here. The textbook I have already uploaded on the Google Classroom, so you can see the textbook. The 5th edition we have. I'm using this one. Okay, as I told you, from edition to edition, there is difference in conceptually. There is no difference. The only difference is in the numericals. The values are changed. Okay, for the exercises as well as in the examples. So it doesn't really matter whether which edition you're going to follow. Okay, so I'm following 5th edition. Okay, but it's okay, you can follow any other edition if you want. So from the textbook, which I have already uploaded over the Google Classroom. Okay, so these are the practice problems which I have written here for this chapter. So with the material that you have covered in the chapter, these problems could be easily solvable. Okay, so I want you to go through them yourself. Problem 1-7, 8, 1-30, 32, 45, 49, 55. Okay. With this, our chapter number 1 is finished at this moment, and I want to take a pause here and ask you, is there anything within this chapter regarding any topic that you do not understand? Please let me know. It was a very basic chapter, had a lot of concepts here in it. Okay, you do not see a lot of problem solutions in this chapter. You'll have a lot of problem solutions in the future chapters. But anyways, this thermodynamic course is a mixture of theoretical concepts and numerical solutions, and obviously all the numericals have theoretical concept behind, then based on which they are being followed and solved. So theoretical concepts are equally important here. So chapter number 1 is done. If anybody want to ask anything in it, you can ask. Otherwise, we will move towards, I will discuss about the assignment right now.
Yes, sir, we can continue.
you. Sir, I have a question.
Yes.
Sir, from which book are these practice problems?
The same textbook which I have uploaded, same textbook.
The one you have uploaded on GCR.
Yes, same.
Okay. Okay.
Okay, everything, because the idea of the textbook is that the whole material should be from the textbook, and the homework problems and the assignment problems and everything should be from that textbook. So we are following the same textbook. All the material will be from the same textbook, okay, which I have already uploaded soft copy. Okay. Anybody else want to ask anything? Okay. Okay, so
No.
let's move ahead. Let me just okay. Okay, I'm sharing with you EES help file, okay, which I have uploaded there as one of the assignment material. Okay, so can you see this on your screen?
Yes, sir, we can.
Okay, now one thing is that, look, this thermodynamics course is a purely and hugely numerical course, and we have now advanced numerical techniques. Okay, so one of the techniques and the software used is specifically developed for the course of thermodynamics and heat and mass transfer, but you can use this software for any other application as well. Okay, and this is EES. It's engineering equation solver, and it's basically nothing else, but it's an equation solver. Okay, so you write a bunch of equations, and then it's going to solve those equations. So it's very simple software, and this software is something which is now being taught everywhere in the world for specifically for the courses of thermodynamics and heat and mass transfer. Okay, now I want you to learn the software. Okay, now the thing is that there are bunch of, if you want to learn the software, and you will have two assignments in this course, and both assignments will be based upon this software. So you will make solution not handwritten but by through this software. Okay, so if you want to make the assignment using the software, you need two things. The first thing is the software itself. Okay, and the second thing is training. You need to learn how to use the software. Okay, so let's first talk about the software itself. The software, I don't think it is available within Zabast, but I'm going to make sure. Okay. Normally, when I was teaching in King Fahd University, it was available there. It's a licensed software, and it's a very small software, but a licensed software. They update it like every year, and the license is also renewed yearly. Okay, so annually the license is also renewed. So I don't think that this software is there in our university, but in Zabast. But when I was looking through the internet, I found of this software, which is a comparatively older version. Okay, but you can use it to learn the software. Okay, and we don't need the advanced options for our case. We just need to. The main intention is that you should be able to learn the software. Okay, so I have already uploaded EES32.rar. This is the software file I have uploaded. There on the GCR. Okay, and what you need to do is that you need to just download it. Even installation is not needed here. Okay, so you just download it, extract the file. Okay, and then run the EES.exe application file for EES. Just run that, and the software will open on its own. Okay, so even no installation needed, nothing needed. And this is a very small software, okay, but a very useful and a very handy software. I use this software during my master's. I use this software during my PhD education, even after postdoctorate. I used it, and I have a lot of publications and material related working on this software. Okay, so it's a very small and a very useful tool, and it is something that with the advancement of the technologies, you should be able to use it. Okay.
So we can use
It
it with any course. Like we can use it for
any
math
any course
solving.
any course you can use it for any
Oh,
course. It's a very handy and useful software. Okay. But the basic advantage for the course of thermodynamics is that it has built-in properties. You're going to use bunch of properties of water, of steam, for refrigerant, for air, and solve you will in this course. However, if you are solving problem over the software has built-in properties inside. You can just directly just put a command and the property will be there with you. Okay. And you can do the solution. So a lot of studies can be done in a very small amount of time by using this software. This is the main advantage of this software, the built-in properties. That's the main advantage of this software for this course. Okay. Now
but
the
will
thing
we?
is,
Can I ask one more question?
yes, yes, yeah.
So, but will we be able to do the solve the equations that we'll be plugging in this
Yeah,
software?
yeah, yeah, yeah.
Will we be
You
learning
will.
them?
Yes, you
Yeah.
will be learning them. Okay. So the thing is that I will be teaching you all the theoretical material during our classes. I'm not going to teach you the software. But when I go through the internet, there are tons of videos, like about more than 200 videos, tutorials over this software. Okay. Now there's a bunch of a crap material which is useless material. Okay. So what I did is that I went through all the material, okay, which is available on the YouTube for tutorials of this software, and I screened and I filtered the useful ones for you guys. Okay. And I put it in the form of a playlist. So Zabest has provided me a Google account, and based on the Google account, on that Google account, I made a playlist, and you can see the link of the playlist here. Okay, this is the playlist which I made. Okay, in this playlist there are how many videos? There are 38 videos, but the videos are very small. Like you see, 4 minute, 12 seconds. Okay, 8 minute. There are only two big videos, 25 minute, 28 minute. Otherwise, 5 minute, 7 minute, 5 minute, 4 minute, 9 minute, 3 minute. So very small videos. If I add the total number of duration of all these videos, that will be about 4.5 hours. So like if you just watch 4.5 hours, you will watch all these 38 videos and you will become an expert in the software. Okay. The software is very easy. It's very easy. It's not like the difficult softwares we have. It's just equation solver. Okay. So it's a very easy software, and I have placed all these videos in this link and in the right sequence. The sequence I have made myself, so that when you follow this sequence, you're going to learn things step by step and things will become easy for you. Okay. Provided you the software, okay, so that you can run the software, you can use this software. I have provided you the software, and I have provided you the playlist over which I have added 38 videos, okay, for tutorials of this software, which are very good, very well made tutorials made by the experts in the field. Okay. In fact, I myself have learned a lot from these tutorials. Okay. So I want you to watch these videos. Okay. So if you, let's say, if you dedicate one day, you spend one day, you'll 4.5 hours, you watch the video, maybe you want to watch the video again, so let's say 7-8 hours, you watch the video twice, that will be good enough. The software will be handy available with you. You can just run the software, you can try, test yourself whatever you're watching in the video. So you can become an expert in the software in no time. Okay. And this is not a difficult software, this is a very easy software. Okay. So I have provided you the tutorials here. Okay. You can just visit my playlist, okay, and go through all these tutorial videos. Okay. It's better if you watch in the same sequence, because it's going to help you understand things much better. Okay. And then you can test your Okay, let me first look at the attendance. We have B140. Is not here. Qazi Muizullah, is he here? Okay. Then we have M. Farooq Ahmad.
Present, sir.
You're here, huh? You will be taking classes in section B, right? Because your name is appearing in section
Yes,
A.
sir. Sir, I'm taking with section A, but the thing was that I mistakenly joined the classroom of section A.
Okay, so you
I
want to
got
take it
to know,
with
so
you,
yeah,
so you will be taking it in section B or A?
section B, section B. I'm from
Section B.
section B.
Okay, and there is Waleed Jamshed.
Yes, sir.
Okay, so Waleed, you will also be in section B.
Yes, sir. So I mistakenly joined
Section
the class of
section.
section A as well. So
Okay,
I'll be leaving that.
and what about Qazi Muizullah? Is he available here right now? Qazi Muizullah is not there. Okay, and okay, Maz Ahmed. No, Maz Ahmed is there in section A. Sorry. Okay. Okay, then we have B130. B130. Abdullah Qazi. Abdullah Qazi is here? No. Okay. B131 is here. Okay, B133 is here. Okay. B1, 133, B138. B131 is here. Okay, B133 is here. Okay. B1, 133. B138 is here. B143, 148. Okay. These numbers, B143, 148, these are what? Your roll number, IDs, or what are these numbers?
Roll
So
numbers.
B is that and 154 and 145. What's our roll number? Registration number.
Your registration number. Okay. B151. Okay. B152. Okay. B152. Farooq is okay. I placed him on the others. Okay. Good. B153. Then B154. B155. 156. 157. 158. So 163. 164. Okay. 168. Hey, Waleed Jamshed, your name is in both the sections. Your name is there. Okay.
Yes, sir. Just left that
Yes.
class right now.
Okay. Okay. Good. Good. So Abdullah Qazi, is he here? Abdullah Zahid.
Yes, sir.
You're here? Abdullah Zahid 131. Let's see. Yeah, Abdullah Zahid is here. Okay. Good. And Qazi Muizullah. Qazi Muizullah is absent, and Abdullah Qazi is absent. Okay. Okay, so let's start with our chapter number 2. You can see the screen on your screen. Chapter number 2 is visible, right?
Yes.
Okay. So contents of it will be we're going to discuss about the forms of energy. Then we're going to discuss about the energy transfer by heat and work. Going to talk a little about mechanical forms of work. Then the most important thing, the first law of thermodynamics. This is the chapter where we are going to develop the fundamental equation of first law of thermodynamics. And then the same equation is going to be followed for the next 3 chapters. Okay, so it will be followed till chapter number 5. So we're going to just apply the equation that we are going to develop in this chapter. We are going to then apply it in multiple different kind of situations in chapter number 4 and 5. So its first law of thermodynamics is going to start here in chapter number 2, but then it's going to continue till chapter number 5. And so the basic equation, inshallah, we are going to develop in this class. Okay, lesson objectives. You go through it yourself. Forms of energy. Energy exists in numerous forms: thermal, mechanical, chemical, kinetic, potential, electric, magnetic, nuclear. So anyways, the sum of all the energies is the total energy, okay, and we represent it as capital E. It's will be in kilojoule. And on a unit mass basis, it's basically capital E divided by m, so it will be small e. If you remember in the last lecture, I mentioned extensive property, intensive property. So capital E is the extensive property, and when you take it per unit mass, so it becomes an intensive property. Okay, so it's specific total energy or specific energy. So it will be E by m. So it will be kilojoule per kg. Yes, somebody raised hand. आपका नाम मैंने नहीं बोला अटेंडेंस में. शामीर. Just a minute. Let me check. 143. No, I placed you present because I was looking the names from the chat box. Not the chat box. The number of people which are showing here. So I saw your name and I put you present. Okay, so basically we classify the energy into 2 basic forms. Okay, and so we have the macroscopic form and then we have the microscopic form. When we talk about the macroscopic form, so macroscopic form are the macroscopic version of energy. We studied this macroscopic version of energy before, in the sense the kinetic energy, potential energy. These are all the macroscopic forms of energy. Okay, so basically the 2 major macroscopic forms of energy that we are going to be covering here, that will be the kinetic energy and potential energy. Kinetic energy is because of the motion, because of the velocity of the object. Potential energy is because of the elevation. Then we have the microscopic form of energy. Microscopic form of energy, but there are multiple reasons for the microscopic form of energy. But anyways, overall, we sum up it to call it as internal energy. So internal energy is a combination of whatever be the factors inside a system for microscopic form of energy. Okay, and we sum it up as, we call it as internal energy. So internal energy is mostly responsible for the temperature of the object. So let's say I have water at 20 degree, water at 70 degrees centigrade. So obviously the 70 degrees centigrade will have higher internal energy than 20 degrees centigrade. Okay, similarly, let's say I have water and I have steam. So steam is something which will have higher internal energy because you need energy to convert water to steam. Okay, so internal energy is something inside. Okay, Abdullah Kazi, you're available now. Abdullah Kazi, did you join late or your call dropped?
सर चैट में उन्होंने लिखा है इंटरनेट डिस्कनेक्ट हो गया था.
अच्छा, okay, no problem. So I put you present. Now there is only one guy, Qazi Muizullah, who is not right now. Okay. So when we talk about the macroscopic forms of energy, so there are two energies important for us, which is the kinetic energy, potential energy. Kinetic energy is like half mv2 square minus v1 square. As a change in kinetic energy. Potential energy will be change in potential energy will be mg z2 minus z1. I mean, this is something that you have covered so many times, I think, in other courses. So there's nothing much to explain into it. Okay, microscopic forms of energy. We can have sensible energy, we can have latent energy, we can have chemical, nuclear energy. Sensible energy is basically the kind of energy which could be sensed by thermometer. Then we have latent energy is a kind of thermal energy which cannot be sensed by thermometer. And mostly the phase change energy is something which is related to the latent energy. Then we could have chemical, nuclear energy. So when you add sensible with latent, so that's a thermal energy. And when you add sensible latent with chemical and nuclear, so all the energies together, they combine up and we call it as thermal energy. Sorry, internal energy. Okay, so if we want to say what is the total energy of a system, so it should be a combination of microscopic and macroscopic form of energy. So it should be a combination of internal energy and kinetic energy and potential energy. So mathematically we can write it like this. Or if we write it on the per unit mass basis, then it will be small u, small kinetic, small potential, or u, small u plus half v square plus gz. Most of the time in our problems, what happens is that we have a system which is stationary. So it's not moving. If the system is not moving, so change in kinetic and the change in potential energy is zero. Because it's already stationary, so velocity is zero, and also it's not varying, and the elevation is remain fixed because it is stationary. So there is no change in kinetic and potential energy for the stationary systems. Okay, so far till here, anybody has any question, anything which is not clear to anybody, you can ask. Okay.
No, sir, no question.
Clear, sir.
Okay, now let's talk about type of energy interactions. Look, we have a system, and the system can interact with the surrounding could communicate with the surrounding through energy interactions. Now, energy interactions between the system and the surrounding can be of two forms. We can have a heat transfer from the system to surrounding or surrounding to system, and we can have a work transfer from system to surrounding or surrounding to system. Maybe work is done by the system on the surrounding, or maybe the work is done by the surrounding on the system. Similarly, maybe heat is provided from the surrounding to the system, or maybe the heat is provided from the system to the surrounding. So we can have energy interaction between the system and the surrounding through these two forms, heat transfer and work. Now, how do we differentiate between the heat transfer and work? How do we differentiate between these two forms of energy transfer? Okay, so the last paragraph written here on this slide is important here. Now look at it. The difference between the heat transfer and work. Any energy interaction is heat transfer if its driving force is a temperature difference. Otherwise, it is work. So if the heat is being transferred, if the energy is being transferred, and the reason for the transfer of energy is because there is a temperature difference between the system and the surrounding, then that kind of energy transfer is known as heat transfer. Now, if temperature difference is not the driving potential for the energy transfer, then we call it as work. This is the generalized definition. This is how you differentiate between heat transfer and work. Okay, so whenever the energy transfer is occurring because of temperature difference between system and surrounding, this is heat transfer. Otherwise, it is work. Is this thing clear?
Yes, sir.
Yes, sir, it's clear.
Okay.
Sir, my internet was a bit unstable. Can you please repeat?
Okay. I was telling that energy can interact between the system and the surrounding. Okay. through heat transfer and work transfer. Okay, now how do we differentiate between heat transfer and work transfer? So if the heat transfer, if the energy interaction is occurring because there is a temperature difference between system and surrounding, then this kind of energy interaction is known as heat transfer. If it is not because of a temperature difference between system and surrounding, we call it work. So that's how we differentiate between heat transfer and work. If it is because of temperature difference, heat transfer. If not because of temperature difference, we call it work. Is this in clear?
Yes, sir, it's clear. Thank you.
Okay, let's talk about mechanical energy. Mechanical energy is a form of energy where some mechanical work is done. Okay, so whenever some mechanical work is done and that is causing the energy to be transferred in or out of the system, that kind of energy is the mechanical energy. Most of the time, in case of the running fluids, it's the pressure of the fluid which is responsible for the mechanical energy within the fluids. So for the cases of running fluids, it's basically we have the pressure energy, which is the flow work. Then we have the kinetic energy of the flowing fluids. Then we have the potential energy. Together, it makes up the overall energy of the flowing fluid. So these are written in the form of differential format and the rate format. Okay, so let's have a problem. Let's see an example here. A site evaluated for a wind farm is observed to have a steady winds at a speed of 8.5 meter per second. First of all, do you understand this word steady? What does it mean?
Meaning the speed doesn't change.
Change with time. So it means the speed is not changing with time. So anything which is not changing with time, we say that it is steady. Okay, so this wind speed is almost fixed for a specific site. Is about 8.5 meter per second. It's not changing with time. Determine the wind energy per unit mass, and then for a mass of 10 kg, and then for a mass of 1154 kg per second for air. Okay, so we are talking about wind. So the kind of energy wind is going to carry, it will be the kinetic energy. Okay, so since we know the speed, which is 8.5 meter per second, so kinetic energy is half mv square. If you want to know part A of the solution, so it is per unit mass. Per unit mass, it will be just half v square. So kinetic energy per unit mass, half v square or v square by 2 is going to give us 36.1 joule per kg. If you want to find out for a mass of 10 kg, then we have already per unit mass, just multiply it by 10 kg. So it's going to give us the energy in joules. And in part C, we need to find it for a flow rate of 1154 kg per second. We already have the specific energy, which is 36.1 joule per kg. Just multiply it with the flow rate, kg per second. So just multiply with the flow rate, kg per second. Just a minute. Okay, can you see the window again? It was actually closed.
Yes, sir.
So yeah, I was discussing that. Okay, so energy is specific energy we determined, and then just multiply that specific energy with kg per second. It's going to give us in kilowatts. Okay, or watts. Divide by 1,000, going to give us kilowatts. So this was the question. Is the solution for this question clear or not?
Sir, C
Yes.
बता दे थोड़ा.
C was that find out the wind energy for a flow rate of 1154 kg per second. So since the wind energy flow rate is given in the rate format, kg per second, so you're going to get the wind energy also in the rate format. So it will be joule per second, that will be watt. Okay. Okay, so the only thing you need to do is that since you already determined the specific energy, just multiply the specific energy with the flow rate. So it's going to give us the wind energy. Okay, in watts, when you divide by 1000, it's going to give us in kilowatt.
Okay, sir, got it.
Okay, there is one specific paragraph here. Let me just give you the gist of it. It says about dealing with energy in thermodynamics. Basically, when we are dealing with energy in thermodynamics, we do not care about the absolute value of energy. Rather, what we care about is the change in the energy. Okay, so let's say we have at certain point we have a certain amount of energy. Then how much is the change occurring within the energy value of that point? This is of importance for us. Okay, so mostly it's delta H, delta U, delta S. Delta values are important. So we are always considered about the change in the energy. So in that sense, the absolute value does not matter. Okay, so let's say that the delta H is 40. So it doesn't matter that the delta H is 40 is because one value was 200, another was 160, or one value was 120, other was 80. But it's delta H which is 40. So absolute value does not really matter. That's why what we do is that we give us how do we get these H values and entropy and enthalpy values? We specify a specific point at some convenient reference point and energy as 0, and then corresponding to that point where we place energy as 0, we determine the energy at any other point. So from that reference point, a specific value is generated for any other state point. Anyways, this was just a basic concept, okay, about the thermodynamic tables, that how the values are coming out from there. You can go through this again yourself. You can ask me if you have anything not clear. Okay, so let's discuss about energy transfer by heat. Okay, so we already discussed that there are two forms of energy transfer. One is energy transfer by work, other is energy transfer by heat. Okay, so if it is energy transfer by heat, so first of all, that transfer must be accompanied because of the motivation for that transfer should be temperature difference. So there has to be a temperature difference between system and surrounding, and the heat always flows from the higher temperature to the lower temperature. Okay, so that's the direction of heat transfer. So this is one thing that we discussed. Now, you remember when we were discussing about different kind of systems. So there was a slide. In that slide, we discussed about open system, closed system, isolated system. And I told you there's a fourth type of system which was not mentioned there, which is an adiabatic system. Now, adiabatic system was a system or is a process or a system where heat transfer is not possible. Okay, so we do not have any heat transfer across the boundary of our system. Okay, so how is it possible practically? There are only two possibilities through which an adiabatic process or adiabatic system is possible. The first possibility is if it is a very well insulated system. Suppose if I have a system and a surrounding, and let's say if there is a temperature difference between system and surrounding, the only way we can make the system fully adiabatic is if we provide perfect insulation, well insulated all around it, so that although there is temperature difference between system and surrounding, yet the insulation is providing so much resistance that heat cannot transfer in or out of the system. This is one possibility. The other possibility, how can we make an adiabatic system, is that if suppose between the system and the surrounding there is no temperature difference. So system and surrounding are both at the same temperature. If this is the case, then in that case there will be no heat transfer between system and surrounding. These are the only two possibilities through which we can actually achieve an adiabatic system. Otherwise, it will never be an adiabatic system. Okay, so either you have a very well insulation if there is temperature difference between system and surrounding, or there should be no temperature difference between system and surrounding. So these are the two possibilities through which we can actually develop an adiabatic system. Is this concept clear so far or not?
Yes, sir, it's clear.
Yes, sir. Clear.
Clear.
Yes, sir.
Okay. When we talk about energy transfer by heat, okay, so we represent it as Q. Okay, capital Q is the total amount of energy transfer, small q is per unit mass. Okay, now there are some sign conventions used in the book. Now sign convention are basically what they are. First of all, they're called convention because there's no specific logic behind it. Okay, so the author decide to choose the sign convention, and then it is a convention, so he follows the same convention throughout the entire textbook. Okay, so maybe if you do not follow this textbook, let's say if you take some other textbook, so the author there might be using a different convention. Okay, so it's just a sign convention, and since we are using this textbook, so we are going to follow the same sign convention which the author of this book used. Okay, and that sign convention is dealing with the direction of the of the heat transfer. Okay, so what it says is that Q is positive. Q positive indicates heat input. So that means if the heat is going into the system, we consider it as Q positive. Q is negative. Q negative indicates heat loss. So if the heat is going out of the system, we represent it as Q negative. Okay. So Q is considered positive when heat is going into the system. Q is considered negative when heat is going out of the system. This is the sign convention. Do you understand this sign convention or not?
Yes, sir. Clear.
Okay. Now look here one thing. Q is equals to positive 3. What does this mean? 3 unit heat is transferred into the system, or 3 unit of heat is transferred out of the system. What do you think?
Into the system, is added into the system.
Into the system, exactly. Now let's see. Q is equals to negative 4. What does it mean?
Heat is lost out of the system.
Heat is lost out of the system. So Q is going, the 4 units of heat is going out of the system. Okay. Now look here. I can write here as Q Q in is equals to 3 and Q out is equals to 4. Now you need to understand one thing here. When I'm just writing Q, I don't know whether this Q is in or out. So the positive sign or the negative sign gives me the direction. But when I'm writing Q in, I am already providing the direction, so I now do not need to write positive or negative. I just need to put the absolute value. So Q in means 3 units of heat going in. Q out means 4 units of heat going out. I don't need to put positive or negative here now because I'm already saying Q in and Q out. But if I just say Q, then I don't know if it is in or out. So the positive and negative has a specific meaning here. Do you understand this concept or not?
Yes, sir. Clear.
Okay. The reason why I'm telling this is because the student gets confused in the book. At some times it's just written Q, and so you see things following the convention, positive and negative. At other times you will find in the book they're already writing Q in and Q out, and then they don't follow the sign convention. Why? Because they're already mentioning it's Q in or Q out. They don't need to write the sign convention. Sign convention is used to specify the direction. If you are already specifying the direction, then what is the point of putting the sign convention? Okay, so if I want to say that 4 units of heat is going out of the system, then I can say this. Q is equals to -4, or I can say Q out is equals to 4. But if I say Q out is equals to -4, this will be wrong. If I say Q out is equals to -4, this will be wrong. Do you understand?
Okay, sir, that makes sense.
Okay. So either say Q equals to -4, or you say Q out is equals to 4. But if you say Q out is equals to -4, that becomes wrong. Because now it doesn't mean that the heat is going out. Okay. So let's move ahead. Okay, when we talk about energy transfer by heat, there are different modes of energy transfer. We have conduction, convection, radiation. So these are the different modes of heat transfer. Normally, modes of heat transfer are studied in a big detail in a specific course of thermal engineering. Okay, so for in the course of thermal sciences or thermal engineering, we study these modes of heat transfer in detail. From the thermodynamic perspective, it's not important right now here. Just basic concept is enough. The conduction is a heat transfer process occurring inside solids. Convection is a heat transfer process occurring within liquids. And radiation is a heat transfer process which occurs between any two bodies having absolute value of temperature or energy in them. So the heat transfers as electromagnetic radiations out of that body or into the body. So this is just the conceptual discussion about it. There are a lot of detailed discussions and a lot of detailed numerical analysis associated with it, but that's not a part of this course. So we are not going to cover it. So that was energy transfer by heat. Now let's talk about energy transfer by work. As I already mentioned you, the difference between heat transfer and work is that if the motivation for the transfer of energy was difference in temperature between system and surrounding, then it is heat transfer. However, if it is not because of the difference in the heat transfer, difference in the temperature, then it is considered as work. So work is energy transfer associated with a force acting through a distance, okay, and in generally work is an energy interaction between system and its surrounding that is not caused by temperature difference. The formula for the work is something you have covered it many times in other courses as well. Really don't need to go with it and go through it here. Work is equals to integral FdS, okay. Work per unit mass can be written as work over mass. Work per unit time is power. It's kilojoule per second or kilowatt. So these are some of the basic informations you already have. Now there is also sign convention for work. But remember, these sign conventions, this is again the sign convention, and we are using it because the author of the textbook have used it in this way. Okay, and these are sign conventions because it is the way author decide to work in this book. It's basically logical. When you're going to go further within this course, you're going to understand the logic behind it. Okay, but anyways, this is a sign convention and we're going to follow the same sign convention. And since this is a sign convention, it's not a fact, it's not a fundamental principle. So if you follow any other textbook, maybe someone else is following other sign convention. Okay, so like for example, we talk about Q, heat transfer. It can go in and out. We can also have work going in and out. So suppose if we have the work done by the system, so we say that system is doing work over surrounding, and so it's work out. And suppose if the work is done on the system, so let's say that surrounding is doing work on the system, so we say this is work in. Now, the important thing here to note is that the sign convention for the work is not the same as the sign convention for the heat. The sign convention for the work is exactly opposite to the sign convention of heat. Okay, so we considered Q in as positive when the heat was supplied in, but when the work is done on the system, we consider that as negative. We considered Q as out as negative when the heat was supplied or rejected from the system to the surrounding. We considered Q out as negative. Okay, and for the case of work, when the work is done by the system on the surrounding, we consider that as positive. Okay, so work positive indicates work done by the system. That's work output. Work negative indicates work done on the system. That's work input. Okay, and again, I will write the same thing again here, which I discussed with you for the case of Q as well. Okay, so I can write here that W is equals to positive 4, or I can write here as W is equals to negative 5, or I can write here W in is equals to W in will be equals to 5, or I can write here as W out is equals to 4. Okay, so work out is considered as positive. Okay, so here W is 4. If I'm just writing W, then the positive and negative sign is going to define whether it is work in or work out. But if I'm already writing work in, or if I'm already writing work out, then I don't need to put a positive or negative sign here. Just the magnitude is enough. Okay, so the same concept which I discussed there for the case of heat transfer is the same concept will be discussed here for the work as well. Is this thing clear so far?
So this doesn't make sense. If the system is doing the work, it's losing energy. So why isn't it negative?
Okay, you're right. Okay, it doesn't make sense to you right now, but later on you will find it will make sense. Let me tell you why. We are looking at, if you remember in the very first lecture, why we are studying thermodynamics. We want to make use of useless form of energy and then convert it into useful output. So our useful output in generally is work out, which we want to represent as a positive thing. You getting it?
Okay.
So in the later on chapters, when you're going to study thermodynamic cycles, it will completely make sense to you, because we want to get positive work outputs. And so work done by the system on the surrounding, you will find out that these are the positive values and they make sense.
Okay.
So it's a sign convention used by the author, but the sign convention itself will make sense to you later on when you're going to continue with this course. Okay.
Okay.
But you have to understand one thing: the sign convention for the work and the heat are opposite. Okay. So when heat is going in, so it's considered as positive. When the work is done by the system, so it's considered as negative. It's considered as positive. Okay. So work going out is considered as positive. And your logic is completely right, that when the work is done out, so that means the system is losing energy. Okay. So, but we are not we are not putting positive and negative in terms of if the system is gaining energy or losing energy. These are the sign conventions we are using based upon what we need in future, the output.
Okay, so I get it now.
Anybody else want to ask anything?
Sir.
No, sir.
Okay. So there's a description about sign convention. You can go through it yourself. Okay. Then there is a description about heat versus work. Okay, there is something known as path function, something known as point function. So there is a difference between point function and path function. Again, from this course point of view, right now it is not that much significant. So I will put it as a self-study topic. Okay, go through it yourself. Okay, when we talk about energy transfer by work, so it could be, okay, work could be done as I told you that the driving potential should not be the heat transfer. Okay, so if any work done in such a way that the driving potential is not the heat transfer, then it is known as work. Okay, so we can have electrical work done over the system. So we have a specific voltage and current. If we know, then the electrical power will be voltage and multiplied by current. Okay, now you have to understand here one thing, that suppose I have a system. So suppose my system is water, and inside the water I have a heater. Okay, so you have an electric heater which is heating the water. So we will still not consider it as a heat transfer, rather we will consider it as work. Why? Because the heat is being transferred to the water not because there was a temperature difference between system and surrounding, but rather the heat was being transferred to the water because the electrons have to move through the resistance wire, overcoming the resistance and producing heat in the process. So there was some work done by the electrons that causes the heat to be produced, which is being transferred to the system. Okay, so it's not coming from the surrounding into the system, rather it is being generated inside the system. Okay, so that's why we do not consider, if an electrical heater is heating the water, we are not going to consider it as the heat transfer, rather we are going to consider it as a work done, electrical work done over the system. So that was just a conceptual thing I wanted to point it out. Okay, then we have different mechanical forms of work.
So one thing I wanted to ask.
Yes, yes.
So what you were talking about right now, if there is a transfer of energy,
Mhm.
that would also create heat, right?
Mhm, mhm.
So wouldn't that create a heat transfer too?
No, your point is completely correct. You have a very logical question, but let me tell you one thing. When we are saying heat transfer, it should be between system and surrounding, not inside the
Oh,
system.
okay, okay.
Okay, so it should come from the surrounding. It should pass the boundary. If it passed the boundary before and then the heat is generated after passing the boundary inside the system, we will not consider it as heat transfer.
All right, I get it.
Okay, got it? Okay. Okay, so we talk about the mechanical forms of work. Okay, so we have different forms of mechanical work. We have shaft work, we have spring work, we have shaft work. When we talk about the shaft work, so we have a shaft. Let's say if the shaft is rotating, so there's a specific torque corresponding to the torque of the shaft. We can find the force. Then we can have the distance traveled by, because it's rotating, so it's 2 pi r n. N is the number of rpm. Okay, so then we multiply force with the distance. We can find out what is the work done by the shaft. Anyways, this is a basic concept here, nothing new. Spring work, for the springs, we have specific stiffness of the spring constant is there, and as we move the spring corresponding to the spring constant and the displacement, we have a specific force of the spring exerted by any spring. Okay, if we have this force, and then let's say that it moves the distance along dx, and then this is the differential work done by the spring if we integrate it over the entire spring, so it will be like half k x2 square minus x1 square. Again, this is something common, there's nothing new or thermodynamic involved into it. We're talking about different kind of works. Okay, so if we have all different types of works available with us, if we add them up all together, so that's going to give us the total work. Okay, so it could be the work of the shaft, work of the spring, electrical work done, any other kind of work as well. Okay, so the theory behind the work and the theory behind the energy transfer due to heat is done. Let's have a break of 5 minutes, and then we're going to start our first law of thermodynamics. 10 minutes, we're going to cover only some basics about that, and then inshallah we're going to cover the rest inshallah in the next class. Okay, so 5 minutes, let's have a break of 5 minutes, and then we're going to start back.
Okay.
Okay, so let's start with first law of thermodynamics. The first law of thermodynamics simply states that energy can neither be created nor be destroyed during a process. It can only change forms. So this is basically the first law of thermodynamics. Okay, so normally what this law means is that whenever you see that the energy is in one form, energy is changing. Let's say a body was moving at a certain velocity. Now the body is actually dropping its speed. So that means the kinetic energy of the body is being lost. So actually, this law of thermodynamics says that the energy is not lost. When it looks like that the energy is lost in one of the forms, so it's actually being converted to some other form. And this law is basically the main law which gives the motivation, because we want to convert a useless form of energy into some useful form of energy. So this law is the law which gives the motivation that we might be able to convert some useless form of energy into some useful form of energy. So this first law of thermodynamics states that energy can neither be created nor be destroyed during a process. It can only change forms. This is the statement of the first law of thermodynamics, and I want you to memorize the statement as well. Okay. The first law of thermodynamics is also known as conservation of energy principle. So basically, we're talking about energy being conserved. Okay, if we write the first law of thermodynamics, which is the conservation of energy, okay, in mathematical form, so it simply says that suppose if I have a system here, let's say this is a system, I have a system, okay. So the system has a specific boundary. Outside the system, we have the surrounding. So whatever is happening at the boundary is responsible for what's happening inside the system. This is what conservation of energy means. So energy going in minus energy going out. Energy going in is happening at the boundary. Energy going out is also happening at the boundary. So energy going in minus energy going out is equals to change in the energy of the system. What is happening inside the system? So this is inside the system. This is energy going in. This is energy going out. Okay, so this is the mathematical form of the conservation of energy. E in minus E out equals to delta E system. Remember, here we have right hand side of the equation, we have left hand side of the equation. The right hand side of the equation deals with the system, inside the system, what's happening. Left hand side of the equation deals what is happening at the boundary. So E in minus E out is something what is happening at the boundary, and delta E system is what is happening inside the system. So let's see each one separately. Okay, so this is the right hand side of the equation, delta E system. Let's see how the system is going to change. Okay, so delta E system means E final minus E initial, which is equals to E2 minus E1. Okay, and when we talk about whatever how much is the change of the energy of the system, so that will be the change at the microscopic level as well as macroscopic as well as the microscopic level. So delta E will be equals to delta U plus delta kinetic energy plus delta potential energy. Okay, so that will be the overall change in the energy of the system. So this is right hand side of the equation. Okay. So delta U will be mu2 minus u1, delta kinetic energy is mv2 square minus v1 square, delta potential energy is mg z2 minus z1. Okay, when we talk about what is happening at the boundary, okay, so that was the right hand side of the equation. Okay, the left hand side is E in minus E out. What is happening at the boundary? So total energy in minus total energy out. So energy can be transferred through the boundary by heat transfer, or it can be done by the work transfer, or the energy can transfer at the boundary also because of the mass flow, because when the mass can go in and out of the boundary, that means it's an open system and the mass also carries some energy. So energy can go in and out of the boundary either by heat transfer or by work transfer or by mass flow. So let's discuss it. one by one. When we say E in minus E out, that means it could be Q in minus Q out. That will be because of the heat transfer. Plus, it could be W in minus W out. That will be because of the work transfer. Plus, it could be E mass in minus E mass out. Energy carried by the mass going in minus energy carried by the mass going out. So this overall makes up E in minus E out. Okay, so that was the left hand side of the equation. Okay, now if you join the right hand side of the equation and the left hand side of the equation all together, so this is the left hand side. If you join the right hand side and the left hand side all together, so this becomes the fundamental equation of first law of thermodynamics. Okay, so Q in minus Q out plus W in minus W out plus E mass in minus E mass out is equals to delta U plus delta kinetic energy plus delta potential energy. Delta U plus delta kinetic energy plus delta potential energy, this is what's happening inside the system. And Q in minus Q out plus W in minus W out plus E mass in minus E mass out, this is what's happening at the boundary of the system. And this is energy conservation. Whatever is happening at the boundary is responsible for whatever is happening inside the system. Do you understand this first law of thermodynamics or not?
Yes, sir. Clear.
Yes, sir.
Okay, this is the basic equation which we are developing right now, but is going to continue till chapter number 5. The same equation we are going to continue from till that point. Okay, now here you have to understand one more thing. Now we are defining Q and we are defining W. Okay, how do we define Q? Q is defined as Q in minus Q out. So we call it net heat input. Net heat input is basically what? Q in minus Q out. So Q in minus Q out is Q. So I can just simply write here like this. So instead of Q in minus Q out, I can write here Q. Is it clear or not, this Q?
Yes, it's clear.
Okay, this is given the name net heat input. Okay, now for the case of work, we define it separately. We write it here as work out minus work in. Okay, this is how we define W, and we call it as net work output. We call it as net work output. So if we define W as net work output as W out minus W in, so here it was plus W in minus W out, so it will become negative W. Look here, so it will become negative W here. So you understand the negative sign here because of our definition of W. That's how negative sign comes here.
Yes, sir.
Okay, so it's known as net work output. That was net heat input. So net work output is W out minus W in, and that's why the negative sign comes here, Q minus W. Plus E mass in minus E mass out equals to delta U plus delta kinetic energy plus delta potential energy. That's the same thing. Okay. So this becomes our fundamental equation. Actually, this is the equation which we will be using now from here onward till chapter number 5 to study the first law of thermodynamics. Okay. At this point, I'm going to stop here, and then inshallah in the next class, next week, I'm going to continue from here onward. Inshallah, we're going to finish this chapter number 2 and the first law of thermodynamics. Anybody want to ask anything? You can ask.
So I wanted to ask about the lecture recording of last class. When will you upload it?
I need a help from you guys because I'm not sure how can I do it. I mean, I saw this lecture on my Google Classroom. There is a folder there, meeting recordings. Okay, but how would I share it with you guys?
So you just need to share the link. The Google Drive will provide you a link, and you just need to share that link with us. And whenever we open that link, we get into that folder and we can see the lecture recording.
Okay. So I will right click on that folder and get a link, and then provide the link to you guys. Right?
Here there would be an option for get a shareable link, so that then you can provide that link to us.
Okay, khalas, I'm going to do this because I was not sure about how to do this. That's why I was not able to do it. Okay. The other thing is that I need your feedback in the sense, are you getting up? Are you catching the course? Are you able to understand the material as we go with the lecture?
Yes, sir. It's easy all up till
Yes, sir.
now,
Yes, sir.
so it's fine. We are
Okay.
getting.
It will need you to you will be needed to do some practice. You will need to spend some time over the material. But the important thing is that uh, my my lecture delivery should be very clear to you. There should not be any hurdle in between. Okay, so you should be able to understand the material very well during the lectures. If you want me to change any of my lecture tactics, you can let me know if you have any suggestion. But the important thing is that whatever lecture I'm giving, you should be able to understand it well. So far, is it going fine?
Yes, sir. It's fine.
Okay. Anybody has any comment regarding anything?
Yes, sir. It's going very well, I think.
Okay.
It's clear, sir. It's good.
Okay. Good. Okay. Okay. Thanks a lot, and inshallah, see you next week. Okay.
Okay, sir. That was.
Okay, sir. Allah.
Allah Hafiz.
Sir.